the next example that we're going to be looking at, sorry, I just want to change into my visor. The next example that we're going to be looking at is an example that talks about conservative versus non-conservative forces. Okay? And it comes from the idea that when we define a non-conservative force changes the mechanical energy of a system. I'm going to say that again. A non-conservative force changes the mechanical energy of a system. There is a natural balance in terms of mechanical energy that says that the sum of the potential energy and the kinetic energy is going to give you a constant value throughout the motion of an object. But if you have a non-conservative force, what you're doing is you're either adding energy into the system or removing energy from the system. Frictional forces remove energy because you have to do work against the friction first, and applied forces tend to increase the energy in the system. So those are considered to be our non-conservative forces. So the example here says that a construction site building equipment is carried in a crate to the top of the building, 12 meters high, using a 28 meter long rope. Okay, ramp. The crate is pulled upward at a constant velocity by a motorized cable that does 103,712 joules of work on the crate. Okay, so a couple of things that I want to mention to you here is that this is also being pulled upwards. So again, I'm going to write down my direction of motion because it's really important. Okay, I have a certain amount of work done, which is 103,712 joules. Okay, and it's done on the crate, and it's being pulled upwards. The other thing I want to mention here is the fact that it's a constant velocity. A constant velocity. Immediately I want to say something. Because of the fact that it's a constant velocity, I know that my kinetic energy of my system will not change. Because kinetic energy is related directly to velocity. So because of that constant velocity that they've mentioned, I know that the kinetic energy will not change. But what is changing here is the fact that I'm pulling this block upwards, which means the height is changing. Okay? The height is being changed in this instance. And height refers to something that's going to happen to my potential energy. Okay? So, again, I'm going to draw a free body diagram just to look at the forces acting on the object. I'm going to place my object on a slope. Fg will act directly downwards. I have my force applied acting upwards. I have my frictional force going that way, and I have my normal force again. Okay, so that's my free body diagram. Couple of points to remember. The normal force, or Fn, does no work on the system. Okay, the normal force, or Fn, does no work on the system. Fg is a conservative force. Fg is a conservative force because Fg is involved in mechanical energy anyway. Okay. The applied force and the frictional forces are considered to be non-conservative forces. And then that note that I mentioned that the constant velocity means that we're dealing with a change in kinetic energy that is equal to zero. So a change in kinetic energy which is equal to zero. Okay. Now, let's look at this. They're asking us to find the frictional force. And to find the frictional force, I'm going to be looking at the non-conservative forces. So sometimes in order to find the frictional force, I calculate the work done by the non-conservative forces, and the work done by the non-conservative forces is going to be equal to the change in my kinetic energy and the change in my potential energy. Now this comes directly from the definition that says that the non-conservative forces will change the mechanical energy of the system. That's exactly what that means. That's the mechanical energy, that's the non-conservative force. For these non-conservative forces, the one is the applied force, and the other one is the work done by the frictional force. And that's going to be equal to a change in that. The kinetic energy is zero because of the constant velocity, and my change in potential energy is going to be equal to mg. The only thing that can change in potential energy is the height. So mg delta H. Okay. Now, when I throw this into the equation, that's my applied force, because that's what they've told us. The frictional force is what I'm looking for. So the work done by the frictional force, that's 0. This is going to be the mass of my object. And the mass of, how much is the mass here? 560. 560. That's 9,8. And the height that I'm changing here is 12. Now sometimes what happens is they don't tell us what the height is. They just give you an angle and a value, and they require you to use some trig to work it out. Okay, so just keep that tucked in the back of your mind. Please also note that when we're calculating work done, we use the distance the object traveled. Now when we're dealing with gravitational potential energy, we actually are dealing with the height that it moves. We're dealing with the height that it moves. Okay, which is where that 12 comes from, and why I haven't used the 28 meters for that particular part. Okay? Alright, now, if I'm going to work that out, I get W, if that gives me minus 37,856 joules. It's a negative answer because it's supposed to be. Yes? You okay with that? Sure. Okay. Now, that means that the work done, I'm going to work backwards, is going to be equal to the frictional forces, delta x, cos of theta, and that then gives me my minus 37,856. The frictional force is what I'm looking for. Now I'm going to use the 28, and that's going to be a cos of 180, okay, which means my frictional force value is going to be equal to 1,352 newtons. Okay, a couple of important equations that we need to just throw in here that I have at the bottom of this page. The first one says that when I talk about the net work in a system, the net work would be the work done by the conservative forces added to the work done by the non-conservative forces. That makes sense, because that's the net work in the system. That net work is equal to the change in my kinetic energy. We have that from the work energy theorem. Yes? We know that will then mean that the work done by the conservative forces added to the work done by the non-conservative forces will give me a change in the kinetic energy. Look at that. I get that from this and this. If that's W net and that's W net, then this must be equal to that, which is what that part is. Yes? Okay? And then, what's interesting is that if we write down what the non-conservative forces are, okay, we can say that, or what the conservative forces are, the work by the conservative forces is equal to the work done by Fg, which is equal to negative change in the potential energy. Okay, and that comes straight from the idea that that the work done by gravity is going to be downwards. Potential energy is always an increase in height. Okay? So when we talk about Fg tends to decrease the height. Fg doesn't make the height go higher. Okay? Which is where that negative comes from. And then the last bit here is that minus change in potential energy is going to be plus the work done by the non-conservative forces is equal to delta Ek, and that's where this equation comes from. Now, I don't really care where the equation comes from. I just need you to know that when we talk about this, the non-conservative forces, that the work done by the non-conservative forces change the mechanical energy of the system. And we know that because of our definition for non-conservative forces. Okay? We're going to stop there.